Hello YouTube, welcome to another one of our videos. Today we're going to teach you how to make a neural network. Let's get right into it. So before we really get our hands dirty, the dataset we're going to be using is called the Mnist Dataset, and it's right here. It's basically made up of handwritten digits, and we're going to train our neural net to classify those digits. This gives us a pretty good indication of what a neural net can do for beginners, and it's going to show you how powerful a neural network can actually be. So let's get into the code. Basically, the coding environment we're going to be using is called Google Colab. So we're going to just type in Colab here, colabresearch.google here. All right. So this is going to load for us, and we're going to get this untitled document. We'll just call it First Neural Network. Okay. So the first thing that we're going to have to do is get in our backend for this program. So we're going to need TensorFlow and we're going to need Keras. Those are actually pre-installed, so let's just get right into the libraries that we're going to be using. So from Keras.datasets, we're calling on import Mnist, which is the dataset we're going to be using. A little space here. All right. Then we call on from Keras import models, from Keras import layers, and this is just going to allow us to call on different types, like basically break down the neural net. And then the last thing is from Keras.utils import to categorical, and we're gonna go through what all of this exactly means in just a moment. So Keras has a bunch of data sets that you could possibly use to help you learn, but Mnist is probably the most useful one. So now that we have those modules in place, we're gonna kind of decide how we're going to split our data set into train set and test set. So this can be done by writing the following code. We go train images, train labels, parentheses, comma, test images, comma, test labels. And we equate that to Mnist, which is our dataset, .load data. And that will allow us to split the data into train images, train labels, test images, and test labels. Perfect. The next step is actually to define the network. So defining the network is really important. It seems like a lot when you see it at first, but it's quite easy. So let's start. We're going to start with network equals models dot sequential, and that's just the type of model that we're going to be working with. We're working with a sequential model. Very easy. And now we're going to start adding layers. So after I add all the layers, we'll kind of go one by one and explain everything. So let's go. We'll say network dot add layers, lowercase, dot dense, a dense layer with input size of 784. Activation function will be ReLU, which I will explain in a moment. And input shape equals 28 by 28. We close that with parentheses, and we are done with our first layer. Congratulations. You wrote your first neural network layer. Great job. So next is the same exact thing. We're just going to copy and paste that. It's two of these in a row. All right, the next layer, which is our final layer, it's only a three layer model. We're going to do network.add, which is our function to add a layer. Layers.dense. 10 activation softmax, which is a different activation function that most of the time neural network models will be using at the end for classification. Finally, we will be doing network compile with an optimizer atom. Add a space here just to make it look better. A loss function that is categorical cross entropy with metrics that we are defining to equal accuracy. All right, so let's break it down. So we add our layers. We'll be using dense layers. Dense layer simply means that the neuron receives input from all the layers in the previous layer. So if we have like 3 neurons in one layer, all the inputs from those neurons will go to the next 3 neurons in that layer. And so what these mean, these layers, is just defining the model and the shape of the model. So where, like how many neurons we have, what are the interactions between the neurons, etc. So once we have this model defined, we'll compile it, and we're trying to basically understand how the model performs. So just to review, we imported our libraries. We defined what part of the data is going to be training, what part of the data is going to be testing. We define our model to be sequential. We say it's a dense model, which means that all the knowledge from the previous neurons will be passed on to the next. We said the input shape would be 28 by 28. We end the model with the final layer with an activation function of softmax. And then we finally compile the layer, saying that we want to optimize an optimizer atom with the loss function of categorical cross entropy, and we want to measure how accurate the model is. So we're not totally done. And if you guys have more questions about, what is ReLU, like who is atom, what is softmax, all of that, we can, and categorical cross entropy and all that, we will be explaining those in other videos, and you can actually check out this video, which I'm pointing to up here, which will explain kind of basic stuff or things you need to know before writing neural networks. So before we can feed our data into our new model, we'll need to reshape our input so the model can read that. So what we're going to be doing is writing right here, train underscore images equals train images reshape. We're reshaping it. 60,000 images, so, and 28 by 28, and that's the pixel height and width, by the way, if you didn't understand that. So we're just making sure that the model understands that our input is a certain size and shape, and it understands how to interpret what we're doing. So we will just define that. I'll explain all of this in a moment. I just want you guys kind of to follow along with me. Test images equals test images. Parentheses, images, and then we can just copy this over. All right. So here what we're saying is, what we're saying here is, boom, we want to reshape our train images, and we want to say we want to tell the model, okay, neural network, you have 60,000 images for training. They're all going to be size 28 by 28. they're all going to be in the same format. They all look the same way in terms of formatting. And then we say the same thing for test images. We say, all right, I'm going to give you 10,000 images, 28 by 28, and this is the format it's going to be in. You might be asking yourself, why are we giving the model more training images and less test images? That's because we want the model to learn as much as possible and then apply what it understands from the vast majority of the data on a smaller set of the data, so that we can understand how the neural network performs. So now we just need to encode the data before it's processed. So we just do this quick definition here. Train labels equals to categorical train labels test labels equals to categorical test labels. Very nice. So what does this mean? We'll use categorical encoding. Just turns the number of features that we have to an actual number of representations, which is really important. So now that we have our data split into training and testing, our model is compiled, encoded, everything's basically done here. All we need to do is just call the fit function to pass our parameters. Basically what this means is we're saying, all right, neural network, this is what you look like, this is what you're going to be taking in as input. Now, this is what you're going to be outputting. This is how much output you're going to be giving us, and this is basically what we want to see from you. So for that, we call on the fit function. We go network.fit train images, train labels, epochs equals 5. What is epochs? If you did not know, epochs is basically iterations, or how many times you're training the model. Like, so let's say the model was learning and then applying its knowledge. So like iterations or epochs is how many times the model is learning and then applying its knowledge. And then finally, we're going to add here a batch size, right? Batch size equals 128. That's just how many images it's taking in. So we're done with the model. Now it's time to evaluate the model. So we'll do as such: test loss, test ACC. Now, one thing to note: what is loss? How do you measure accuracy? I think accuracy is pretty straightforward. The model kind of looks at an image, says whether it's in our case, it looks at an image of a 6, says whether it's 6 or 7 or whatever number the neural network interprets it as, and it's kind of like a more binary type of accuracy. Like you either got it right or you either got it wrong. Loss is, it's telling us how inaccurate at times the model is. So when is there error? And the whole goal of a neural network is to adjust the structure to minimize loss. So that's what loss and accuracy mean in this context, because they can mean a lot of different things, especially in this field. So we define test loss and accuracy as network.evaluate, very straightforward, test images, and test labels. All right, and then we just finally print our test accuracy, test ACC, with our actual test ACC, and then just the same thing here. So just the test loss string, test underscore loss. So these are parameters for measuring how well the model is working. And now we're going to actually see how the model performed. Now you can play with all these numbers, right? You can change atom, you can change categorical cross entropy. You can do a bunch of things here. You can change even structure. You can play with the activation function. You know, ReLU is just a standard, you know, and then softmax is a standard, but like for the final layer, but that doesn't mean that you can't play with it. Just for now, since you guys are beginners, or if you're not a beginner, just this specific video is focusing on how can I build my first neural network and how accurate can it be. So now let's see how our model performs. Oh, forgot to add a equal sign here, my bad. Equals. Let's run the model. All right, so now you can see that our model is running, and you can see the accuracy right here. It's going to be an epoch. You see the epoch, and you see the accuracy, and you see the loss. The loss you will see is gradually decreasing. The accuracy is gradually increasing, and you see the accuracy here is tremendously high. A, because our sample size is massive, and B, because the structure of the model is very simple and it's fitted to exactly what our task is, which is image classification. So you see within 3 epochs, this is almost at 99%, which is insane. And most neural networks that you will work with will not hit this level this quickly, just because this data is engineered to be manipulated with within a beginner's. Thank you guys for watching. If you want to see more videos like this, make sure to subscribe and like down below. Peace.